So you might or might not know, but Accelera has it was founded in 2006 with the idea to have a lot of with the idea to kind of transform or try to transform biomedical research into drug design by using computerized drug design. So to use the term computerized more often through simulations. And the first thing we did was the SND, which was at the time substantially faster than anything else that there was back then. It was around, one GPU was around like 200 processor in AMD in terms of speed. But it's not the same now. Now I think GROMACS is 10 CPUs more or less the speed of a GPU. I think this is another one, another big evolution that will allow us to kind of get closer to that sort of vision where you routinely do computerized drug discovery or computational biology, and it gives in our hands, it gives substantial speed up, so at least a factor 10, which is great. It's still probably not enough. We'll hope Moore's Law will help us a little bit there in the next few years. As I told you, HTMD was built for this, so we expect it to be as easy as possible. And so, I'll just tell you what is that it does. What's the concept? So, instead of running a single simulation, this class, which is adaptive runs, this Python class object, will execute adaptive runs on a given resource. So the resource can change. It can be your local computer, it can be a cluster that you have in your institution, or it could be Amazon. It starts from a set of initial configuration, which can be 1 to 10, 100, whatever. Let's say that we have, because you need to equilibrate with all of them and so on, it's usually between 1 and 10. I suggest you don't use 1 because something might go wrong during one equilibration. There will be some sidechain flips and it should not have flipped. And so if you have a little bit more variability, then it's good. But it could in principle start with 1. And these simulations inputs are just represented by directory. So each directory is a new simulation, which you could simply say, in our case, we use SND. SND is not, it's kind of natural here, so it is, in theory, all of this is MD agnostic. So you could use any MD software. The concept is valid for any MD software. There's nothing special in MD. In SND that allows this. So HTMD can drive in principle everyone. In the future, we might well do that. Because it's so young, it actually only works on SND, but it's relatively straightforward, I think, to extend it to other codes if one wants. So these input directories are just directories on which you will go in and type SND input and run, or AMD input and run. And generating simulation, in this case, by building a Markov model of the data on the fly. So just run the simulation, retrieves them automatically, builds a Markov model, and using some criteria, there is not yet an optimal way to decide which is the best criteria to use. So we'll use one, but to show you, you might well use another one. For instance, the criteria we use is general and valid on every single victim. But you might know that there are some mutations in your system which tells you which contact is more important than another one. So you can try to decide adaptive schemes which are more clever because they have more specific information. So tomorrow, with Stephanie, you will write your own adaptive scheme based on HTMD, be it by favoring some distances or other things. The one I present here is agnostic, so it works for anything. Okay, this is a publication that where we first applied this. I showed you some graphs before, and in the paper I sent around, we gave around, there is a more generic version of this. So Adaptive takes one or more generator simulation, which is a directory, and practically decide which are the new input coordinates from which I should start this. The system don't have to be identical. Of course, it makes sense that they're identical in the sense that you always want to work the same problem as a ligand, for instance, if it's a ligand protein system, but don't have to have the same number of waters or so on and so forth. It's able to recognize these things. So you could have 10 initial simulation and they all have more or less the same amount of water, but maybe 3 less in one, 10 less in the other, or it doesn't matter. So the way you set set it up, you create a directory, and inside this directory, you create subdirectory one for each simulation. So it's very easy. And these simulations, instead of launching, let's say I have 10 simulations, I could decide I launch 1,000 from this by replicating 100 each individual one. And this is a possibility. But then you kind of finished your compute time, for instance. So what this does is, I don't run 1,000, I run 10, or I run 20. I just replicate twice. So you run all 10 twice. And then there are epochs. What are epochs? So what you do, instead of running, you decide that, at least this is the way it works here. You decide that you have a windows of runs. So you want to run 30 runs maximum, but you want to have always 20 runs running. So between 30 and 20, you should always be, you should always have this sort of window. So the system will run, and will decide if you are within this window. If you are below 20, which is your minimum, it will then analyze the data and submit up to 30. So build up your queue up to 30, which is the maximum you get. Every time you analyze and do a response run, we call it an epoch. So you can decide how many epoch analysis you do. How long should your simulation be? This is system dependent. They don't have to be a microsecond. They usually have to be of the order of 10 to 100, 200 nanoseconds. Depends. The shorter they are, the best is for you and for the lattice key, so the more you gain. If you could run very short ones, that would be really convenient. But there is a limit that you need to be in a regime that the Markov model is converging, and in order to get something out of it. So, as a rule of thumb, for ligand binding, for GPCR we use something. Ligand binding or GPCR we use anything between 50 and 100 nano each simulation. And for trypsin examining, you can get away with 10 nano because everything is very rigid and so on. If you have a lipid-like molecule binding through the membrane into GPCR and so on and so forth, you're probably gonna get something if you are in the 200 nanosecond time scale, because I believe is the knowledge. It all depends on your projection. So maybe tomorrow we find a better way to project lipids, also to take into account the lipids configuration, which is blocking the entrance and so on. And so your Markov model will become memoryless in much faster time scale. So you don't need to run for 200 nanoseconds. At the moment, this is what we use. So on the order of tens of nanoseconds. So only the coordinates files are seeded. So if you run for a few nanoseconds all of your trajectory, your 3D trajectory, and then we do an analysis, and we could retrieve the velocity as well, but we don't. It's not necessary really, because you lost your memory already. It's on. And so what we're doing is we're just taking the coordinates file from the TCP or the XTC file, whatever you say the trajectory on, and we use that to seed the new simulation. So we don't have the velocity, and so what you need to do is to generate the velocity from just an Maxwell Boltzmann for instant distribution. So you just assign a temperature, and this is okay. Okay, so we run a sample, and all your machines, all your virtual machines, or your Amazon machine have one GPU. So you can run SMD on those ones. I think I need to activate it. It went up. It told me before that you guys need to activate it, so we can try to see if that's still the case. So no, I think it's fine. So you need to run this notebook. So create a new notebook for your virtual machine. Type that thing, and that should give you a license for 20 hours, I guess. And
sorry, can you say that again? We need to do what?
Type this in, and unless you have it, I don't know if you have it. So it's in the file system, so you just open it. And execute it. So while you do that, so practically you need to go here. There will be something like activate SMD. You click on it. This will open, and then you run it. This just activated SMD on your node, and for X amount of hours, and so you can run it. So the build system is all streamlined, as you saw. So the second thing you have to do after you build something is to equilibrate it and set up your production rack. And again, even here, we saw that in the lab, there wasn't some criteria, but everybody was using his own. And so we said, oh, this is a good opportunity to kind of abstract it out. So you don't need to know anything about ASMD or whatever MD code you're running. You don't give a damn whatever code you're running, you just want to run it. And there are quite good parameters that you can set most of the time, especially for equilibration. So this is what they're trying to do in this protocol. So we could think that there will be more protocols in the future. And this is quite new, so we just have the first protocol. And the way we divide the protocols are in HTML.protocol, and we don't pre-import it because you can imagine there will be an equilibration version 2 in 3 weeks, but you still like to use equilibration version 1. So you import whatever, so the class definition will be the same, the implementation will be different. And so at the moment we are all in version 1, and maybe tomorrow somebody comes in the forum and says, oh, there is this is a better way, and this is a better way, so we can change the default for everybody. I think this is a good way. So I'm going to try to use. I was actually first going to try to use the new appeared receptor, so set up an adaptive scheme for the ligand in the new appeared receptor, but then I thought that Barnase/Star was better because the guy just built it. So the fact is that I'm using this directory, so if you're not in that, you should check if you have it or not. So if you open a terminal, and the only thing you should have in the terminal is impossible to see, but is a build directory. But I don't know where you can use it. So you might not have this one. You probably have build BS. Build BS. So create a directory mkdir /temp/barbar and copy the bar BS into this directory and call it build. So the command would be so just mkdir temp barbar and then you do cp-r temp build BS. Or in fact, we could simply move it. Move.
So this virtually, what was it again? Build what?
Build, you should have it in build BS, because with the previous example, I don't know, maybe where do you have? Do you have a bar directory in your temp or not? No. Do you have a bar BS directory?
Build BS.
Build BS, sorry.
If you run the example of the last session.
So another way, maybe let's do this way then. Let's go here. You go to here, exercise. You get this, and then you just do cell run all, and this will create your Barnase/Star here. I hope.
Well, there should be structured PDB file. That's what structured PSF as well. And yeah, it's fine. Yeah, no lines. It's build slash temp slash build PS. I think it's PS. I'll just leave it as PS. No, it's it. The camera is there.
It's the voice.
Can I just kill that? Maybe do one?
So once you've done that, in your build directory there should be a PSF file, a PDB file, an input file, and probably that's it. And a parameter file.
The actual example we're working now is adaptive sampling. Adaptive sampling, is that correct?
Sorry?
The actual example we're working on now is adaptive sampling, is that correct?
Yes. But I don't think you have the latest version of this presentation. My presentation in your VM. So this is what you have. This is the end of the build system. That's what you should get inside the build system. And you should have a parameter file, structure.pdb and a structure.psf.
So that's good. I just made that mind object. Otherwise,
In this terminal, is there a way to copy and paste anything?
What?
In this terminal, is there any way to copy and paste anything?
I haven't found one.
Right click.
this is what should be. You have it. You have. I had a thing called build VS. Yeah, all these files are in slash time. You don't have build VS. Random session thing. And then you rerun the command to. Yes. You rerun this command to input files.
So I assume most of you have that on. Okay, so if you want to rename the directory, these files are not in your computer. These files are in the Amazon cloud. You cannot open a terminal in your computer and see these files. You need to open a terminal in the Amazon computer. And the way to do that is by opening a new terminal. So what I've done here, I've started the HTML and I decided which protocol to use, which specific version of protocol to use. And I said, well, my path is this one, where I have all the files.
Sorry, this is the directory in which these files are supposed to live that we created earlier.
Yeah.
Correct.
So if they are in build VS, you specify build VS or you specify one top? Or will it be the barbar?
The buildings will be is for me is inside bar.
Barbar.
Inside barbar I have a directory which is called build, where I built the system before.
Yes, and it would automatically pick that.
Well, I'll tell you later where it is. This is my route where I will work. From there I will work. Because I need to create several directories, so I want them all to be in there. Okay, so I started md.equilibration, which is taken from equilibration version 1. And the way you set specific parameters is by simply setting. So for instance, I say, well, I want to run for 10 million steps. I want to run for 10 million steps. And I want the temperature to be 300 Kelvin. So let me set this up. This equilibration also has the possibility to set up a flat bottom box. What's a flat bottom box? Is, let's say you want to have a ligand and you want to restrain it in a certain box. It's typical in a GPCR that you don't want the ligand to be in the intracellular part because you're using a periodic box. If you leave a ligand above, it will just go anywhere. So you set a patch on top of the GPCR where you say, I just want it to be in this northern side of the system, but not go the other way around. The way to do that is to set a potential, a restraining potential on the ligand, which is flat, and then it goes up, like with harmonic normally. Then you can do that in X, in Y, and in Z, and you kind of limit the area where the ligand can go. So I don't use it here because I don't do the GPCR anymore. I'm doing the Barney pasta where I don't mind where they go. They can go anywhere. And but so you can use that. And this is centered on a certain specific location. So for example, that GPCR, because the GPCR itself can move in the membrane, you don't want to fix in a specific dimension in space, but you want it to be centered on some atom in the GPCR, so it follows the GPCR, for instance. And so, yeah.
So if I actually execute this command, can I undo that somehow? This flat bottom potential definition in the box.
Is somebody connected to the AWS data server? Yeah. Because I think this thing is refreshing. You can redo it by restarting this. Re-executing that. So there is a documentation in equilibration, but this what allows you to do is to give a centered reference atom, to give a selection on which you want to apply the bounding box, in this case the ligand, and the box as with the origin in this point, or the central mass of this point. Okay, so this is kind of centered in GPCR, and I said I want something like that on top of the GPCR. And then the constant that you apply in that.
Which would the paths actually keep receiving because most of them have it in BarBS and they haven't managed to copy it in BDPS.
Yeah, but that doesn't work for me. Then it doesn't work for me.
Well, so they know what to put in maybe.
But put.
No, this won't work.
If you can't copy this into bar, then the reference path should be temp. It's saying that somebody cannot copy this. So then you use the reference path. Okay, so if I'm in a GPCR, I want to keep a constant, when I apply the equilibration, I want to keep a constant XY dimension in the membrane. I don't want it to squeeze it like that or like this. So I just use that. And because I'm doing Barney's bar stars, so protein-protein interaction in solution, I don't care. The whole dimension can can change independently, so I use false. And then we have this write command. And what this write command does, to give an input directory, which the directory in which I can find my file, structure.pdb, structure.psf, and parameters files. Because you generated with HTMD, it kept some standard naming, like structure.pdb, structure.psf, and parameter. So I know what to look for. And then you say where I want to put my simulation file for the equilibration. And in this case, I want it there. So what this does, it sets everything up for you. So you haven't even seen a manual of HMD, and this will work. So this will set up a proper equilibration. What I mean by proper, if you set up 40 nanoseconds of equilibration, it will split 40 nanoseconds in up to 20 nanoseconds. It will progressively reduce the constraints on the protein. Every carbon alpha on the protein starts with 1 kilocal mole constraint, local constraints, because you want to preserve the crystal structure. Every other non-carbon alpha but still heavy atom will have a 0.1 kilocal mole constraint, and this will go down up to half of the simulation to 0, and then while the pressure is the barostat is working, and from there onwards it's totally free. So you have the other half of the simulation where you just running the barostat without anything. Is this the best protocol? No. It's the version 1 protocol. It works pretty fairly good for us. Yeah.
Have you tried with DBCR?
Yeah, DBCR. So if I go here now, you can't see, but there is an equal directory. And inside I have an HMD input file.
Where can we find the structure that will be in PSF?
Where?
Where can we find those files?
Where can we?
Where are we looking for the files? Like we haven't downloaded any.
Which file? Structure.pdb, structure.psf, where in your build directory?
I'm going to find the PSF files.
Just to be clear, where Johnny has temp bar, you should probably just have /dmd.
Or you copy the build, yes.
Or you copy everything there.
Yeah.
That's right.
There is a difference between building and equilibration. So in the building, you created the PSF file essentially, and this has been done in the previous session. Or now, if you run the solution output in the new step, md.new. It's small, but in this case, it's just equilibration. So it's just one.
But you can split it into, like if you wanted. I had it open longer in the other PS.
You can do whatever you want, just save it in the directory. Okay, so I never ran this, so it might not. I don't know if it doesn't run, it's because Stefan did a mistake.
Yeah, I think he has.
Did he?
Yeah. Didn't change the variable. So can't find the code. In this one here, where it tries to make these folders, no, it looks good for like build right here.
Oh, you're running it like this. You don't want us to run through the.
No, just as you said, it's not working, but it's actually working. So I'm now ready to run because I built the calibration directory with everything in there, just the file I need, the input file, the PDB file, the PSF file, and the parameter file. And so, and then I decided that this could be SMD my cluster, or it could be SMD Amazon, in this case SMD local, which happens to be in an Amazon machine, but it's practically local to the machine. It will use only the GPUs that is there. And they say, oh, found one GPU, I found SMD, and it's running.
Not really. We've got a variable error. There's a problem.
Okay. If you actually go to the terminal,
There's a problem.
you can see that there is SMD running
When I
there.
run inputs, right, you have no it doesn't like the variable. So it doesn't like this variable. It cannot find this coordinate.
No, that's
So it's supposed to declare.
So this will come out.
Which one has to be printed out? Oh, so I just remove this.
Yeah, remove this for lines. These are for platform potential, and since it's not
So restart from here.
She's not activated yet.
Yeah. Yes, the flat bottom here has to be connected up. And then you restart. This has to be entirely has to be this whole has to be no, but it's not in the version. No, it's not commented out. That's why it's giving that error.
So in the version you have, apparently this is not commented out. This because in the version you have, I was going to do the GPCR. This is not needed. And in fact, if you do it, it doesn't work because it doesn't find this thing. So you need to start and build the calibration. This is just for explaining you the plot model. Use that. And then this is still running, and it will run for a while because it will set it up to 40 nanoseconds. And there is a wait here. So if I hadn't put a wait, it would have just gone, the SMD would have started running, and my Python shell was free. So the way I put the wait there, because that's the way I usually use it, I just put wait and then the preparation, the production, by running the after. So I stop it now, so that I can. I can test. I can do the other things. The stopping is by here. Interrupt the kernel. So I assume this has finished. And when the simulation will finish, the MD, the weight will come out, and so we'll keep going. So you could execute this all at once. For equilibration, the same as for equilibration, we have the production. And the production is kind of the same thing, but it's simpler because you have less things involved. We never use an MPT for production. And so we always run in an MVT ensemble. The reason is that with the system size that you get today, there is no reason to use MPT unless you're doing some really odd conformational changes or really brutal changes inside it. All ensembles are identical. All the equilibrium probability or equilibrium distribution of all ensembles are identical in the 1 over square root of n. So it's identical when you have a lot of atoms, unless that lot of atoms are not that much compared to what you're doing inside. So if you have a huge protein which is folding and very little water around, then that's a problem. The Barostat was really important 20 years ago when we were doing argon on a system of 10 angstrom by 10 angstrom, and then that was a bit different.
And the referees are fine with that.
Yeah, it's 8 years that we're publishing it. And it's actually better because when you apply the pressure, it's not necessarily the best thing you do. You're stretching every atom position and so on and so forth.
Unless you have an anisotropic system where you want to, unless you have an anisotropic system like a circuit or anything that you might want to allow it to equilibrate.
But we do equilibrate with the pressure. We do equilibrate the Barostat. So if I remember protein, we usually equilibrate for 100 to 200 nanoseconds. And that's enough to make the volume constant and nothing will change after that, apart from fluctuation and so on. And then you can just run without any problem. Okay, so I'm going to use production version 1, which is actually something that's very, very simple, but I'm going to show you a little bit more how it works. So, and by showing a little bit more, I need to show a little bit of what's happening underneath. And underneath, I'm using SMD, and if you use SMD, you see that these things look quite familiar. So practically, what is MD? What is production? Is a class, and the member of this class are the commands that you use in an input file of SMD. So you can just simply edit those and set it as you wish. For instance, you could decide to change some of these parameters, and then when the write function acts, it will transform this input file of SMD. So, for instance, you can decide to change the bin coordinates and the extended system, and you don't want bin velocity and you don't want bin index. So if you're not familiar with SMD, it's pretty similar to NAMD. So bin coordinate is just the coordinate file, the .core file that in the binary format that you start from. Extended system is the box size, which you got at the end of the equilibration. And that's why I call it output.core and output.exe, because we want to start from the end of the equilibration. So at the end of the equilibration, the output was called the equilibration. At the end, produced some output, which is output.core, so the final system, the output.exe, which is the box size after the Barostat, and also velocity. But I'm not going to use the velocity because I don't care, because for the adaptive, we don't use the velocity.
So if you do not specify these two lines with none, it will automatically write out by default the bin velocities and bin index?
Yeah, the defaults are the one you saw here, so I don't know.
No, but you don't.
So when I start and of production, I already have some defaults, which are the ones you see here.
Yes, but bin index,
They're not there.
they're not there.
Yeah.
So why are you specifying?
Well, just to show.
explicitly?
Yeah, no.
Okay, just to show.
Also, this could change in defaults in a way. It's a bit ugly because we need to specify SMD specific parameters. Ideally, would be that you don't need to know any values and you just run. But at the moment, we do it this way. Let's see if later we have a version 2 production which abstracts out SMD. For the calibration, it's already the same thing. The calibration.smd will show you all the parameters if you want to know more and want more control. But you shouldn't need to. While in this case, it's needed still.
Excuse me, in the code we have there's at the end of the command where it says empty box, and then the numbers there look suspiciously similar to what we saw earlier that you commented out.
The presentation you have in your virtual machine, the virtual machine was created yesterday or whatever, so it's not the same as the one I'm showing.
Okay.
So if it's not identical, you need to see whatever I'm using here. And okay, so I say I want to use, I've done the calibration, I know that there is an output.call file and output.xsv with the box dimension. I don't care of the velocity. So I said that these are what I start from. And well, it doesn't work because there is no output, because the simulation is still running. But what this would do is pretty peculiar, and we did it this way because we didn't want to. So when the output, let me do this actually, a little trick. Which is finished, so it should be there. There is output. What do you want? So what this is doing is simply saying, I generated some output.64 and output in the box dimension. I pick that, I pick the structure.pdb and so on and so forth. I create a new directory. In this new directory, I have all the production running. And so what is generated is again another directory inside the generator. I only start with one initial directory. So inside generator, I have one directory called simulation1, but you could have created with a for loop as many as you wish. And this has an input file, a parameter file, a structure file, and so on. And in this case, the input file is this one. But we don't care because we... Okay, so now we have a directory for running our production. Okay, so we could just run it and see what happens, or do it in the adaptive way. So let me create a new directory which already exists, so it goes out, and I cd in this directory. Okay, so I'm inside this this directory now, which is empty. So I'm inside this directory, which is empty, yeah?
Checking the log file, it says it was finished last Saturday. The actual page is still okay, or is there something wrong with it?
No, it's just too long. I put 40 nanoseconds, I think.
40 nanoseconds.
Yeah, and the Amazon GPU are not really fast. You can reduce it. You can reduce it. You can kill it, and then. No. Well, yeah, you should. This is the real thing I was using. So this is an important bit. It doesn't matter what. Sorry, guys. It doesn't matter what happens up to now. What we did was we took a build system, which was I built some structure of PSF, PDP, and so on. This works the same in Amber, by the way. If you build in Amber, that's fine. And then we create an equilibration directory automatically by setting 2 variables, and we run that, and then we create a production directory. This production directory has everything already equilibrated in the system. So at this point, why I have this one? I modified before. Sorry?
Two forward slashes.
No, I'm saying here that I modified this and now this is still here. So this is all you need to run once you have the directory to run. That's all you need to run an active run. Okay, and then this you can leave this notebook open for a few days if you want, and this will keep running. So first you create an object that active run. Then you say I want between 2 and 4 simulation always running. And I want 30 epochs. I told you already what an epoch is. So a successful event of analysis and risk. And where do I run? Again, SMD local. We run on GPU grid, so we'll put SMD GPU grid. Or if you have Amazon, you can say SMD Amazon, and so on and so forth. Dry run, I just use it here, so it creates everything but does not submit anything. So if you remove this, it will actually run for real. We could be, and the default is to run for real. So we could be kind of, will not run anyway, but this I modified. I don't know why I have this version here. So because Barney's bar star, one is in chain A and one is in chain B, and we want to speed up the recognition between these two things. So we want to create contact maps between these and recognize which contact maps are under samples or which one are more important and so on. So in metric selection 1, I say that I will compute the contact maps between name CA and chain E. So all the carbon alpha of Barney's. And in metric selection 2, I will use name CA and chain B. And metric type, I will use contacts. What does it do? It says, but what this is saying is, when you go and analyze your system because you have less than 2 simulation running, what you need to do, you have to take all your data and project it on the contact maps between selection 1 and selection 2. In this case, Barney, contact carbon alpha Barney's and carbon alpha. The default is an 8 Armstrong cutoff. You can change that, but 8 Armstrong is usually fine. So everything that is in contact between the two proteins will create a contact map. If they are further away than 8 Armstrong, will be a 0 empty matrix contact map. All the simulation will be transformed in this sequence of contact map. The system will do a clustering, as we said, to get discrete trajectory. It will build a transition matrix. It will diagonalize the transition matrix, build a Markov model, and compute some Markov model, compute some criteria to assess which area are less sampled. And the criteria is that we simply try to sample equally because we know nothing about the system. So if I have a well here and I have another well here, I just try to make sure that.
Sorry, so is this actually only just another version of metadynamics then?
Nothing to do with metadynamics, fortunately. And the reason is that we don't bias the system at all. Okay, so if you get these coordinates wrong, your data is still good.
But you bias it insofar as you choose specific
starting points
to carry on.
Yeah.
So that way you bias.
I pass where I want to sample, and maybe I'm really bad in which degrees of freedom I want to sample. But the degrees of freedom are really general here. I'm just saying context, just get in touch and see.
Based on your experience, where do you choose those checkpoints that I want to sample from? Just random?
No, it's automatically chosen from your example. You just say which projected space you want to work on.
But so if you have a brand new system, which you do not have no information, how do you actually decide what
we always use this. So if it's a ligand with a protein, every atom of the ligand against the carbon alpha of the protein. If it's a folding, it's carbon alpha of the folding against itself. For us, contacts, it's what works the best. You might be more clever than that and find. So it's very easy to set this up. There's no thinking or anything. You just decide this against the other. You could try to find, as I said, in case of lipids, in case you have a lipid drug which is trying to enter through the membrane, lipids are really slow to move. And we're not, if you put the atom of the drug, lipid drug, against the atom of the GPCR, it's not such a good reaction coordinate because you have things in the middle which are really sticky. And so that's why we need longer simulation, 200 nanosecond simulation. Maybe you work on it and you say, no, we can also consider the lipids somehow by extending this metric into some sort of other general way. Then instead of needing 200 nanoseconds, you get back to just 20 nanoseconds. But the reaction coordinates we're using are really, really general. There's nothing you need to know or think about the system. If there are two-body system, in what sense it could not be well? For instance, trypsin benzamidine, and you put a lot of ions. And the ions will bind, they will compete with benzamidine. But you don't have, the poor Markov model does not have any way to see that. Just sometimes, coming from this contact position, it goes in very quickly because there is no ions in the bound pose. Sometimes there is an ion already bound there, and it goes to the same contact, but it never goes in. It just goes out. In that situation, you need the Markov model as a memory because you have to average out those degrees of freedom that doesn't see if the ion is present or not. And so you will need a very long simulation in order to average those out. This is an example where just contacts between these two don't want.
And when, in your experience, of course, is you say that, okay, fine, this is what I'm going to stop my simulation at, and I'm not going to get any more information beyond this point.
So the question is, when do you stop? And let me see. Let me finish this. So,
Okay.
on top of this, we just apply a further dimensionality reduction, which is now standard. Everyone in Markov model should use this. It's called time-independent component analysis. It kind of selects these lower degrees of freedoms and project on that. It works really well. And in this case, we just project on 3 degrees of freedom. It's probably not enough for a product-product interaction. We can go between 5 and something like that. I think if you use 5, it's okay. Update period.
this script does not exit. This does not exit and just runs every 4 hours. So every 4 hours we check how many simulations are running. Oh, it's just 3. Okay, nothing to do. It comes around 4 hours and say how many simulations are running. Oh, just 1. Okay, I need to do the analysis. So I take the data, I project everything, I compute the cluster, I compute the Markov model, I decide which will respond, and restarts the simulation. This is pretty general. So this will run, all your system will run in something of this form. That's what we're running on the timeline. So when do you stop? Well, one day in the morning you wake up and say, okay, let me see how it goes. And you'll do an analysis, which will be shown tomorrow, how to do Markov model analysis. And you see what you see. You can see that the implied time scale are perfectly converged, so your Markov model is converged. And you get some numbers. And of course, the Markov model sees only as much as it sees. The slowest process in a protein ligand binding is the folding and unfolding of the protein. You don't see that process most of the time. So you just looking at the ligand binding, you think this is the process. There's never an end. Depending what you want to see, you will see it earlier or later. So you just do the analysis every once in a while, but this runs pretty unattended. And every once in a while, we run it for months. And then after, once in a while, we go and we look, this happens, and let's see. Or we already have some results, we understand what's going on, we run some more simulation here and there, or we try to understand something, or we build it. So, So in this case, the execution was within the notebook, which is convenient but also inconvenient. Inconvenient because if your cron crashes, then the thing stops. And if for some reason, some simulation, especially for us that we run on distributed computing, if some simulation is broken, some data is broken, maybe for some reason the system crashes, then the stuff stops. So this is good if you run for a few days and you don't want, and you have everything there. So I now happen to have all the build system, the calibration and so on, the production ready on one page, and then I have analysis and adaptive on another notebook. So I just run the adaptive, and it's always running, and then afterward I have the analysis. So when I have to do the analysis, I just run there and do the analysis. But adaptive will also crash, right? If your Chrome crashes.
Yeah. So this is you might stop so you don't realize it because So what's the second way? So when we run for a really long time, we use a cron. And so this is the best way to do it. You just, if that's your adaptive bit, so that's 7 lines, you just set a cron which runs every 4 hours and which runs this. So you practically so this is the bash. This is the cron.sh file which runs Python conf. It's important minus login because you need to import all the Python bits and so on. And then you do cron tab -c and you add this. You cd wherever you are and you run your cron. And this will run forever. And we have sometimes 4 or 5 crons at the same time, so we even have to change the hour in which they run because this might consume a bit of memory. So you don't want to add that. So this is the alternative way. You just set up a cron which runs your Python script against a Python script and run whenever you want, and then you forget about it. And then this will create the data and you will load the data. So I think there's nothing more here, So summarizing a little bit. Unfortunately, we have this misalignment between I thought I had modified this script to save in var names in var, but I don't know why even my script were modified. So in the previous section you saw how to build, And that's quite long and complicated because there is some part which are simply PTB manipulation. You want to move the structure, rotate it, place it where you want, assemble it, and so on and so forth. And it can be made very simple if it's system specific. So if it's for GPCR, for kinase, and so forth. After you build, you need to equilibrate. Equilibrate is very easy. And you can see that equilibration script is not good enough for you, but then you can look at it and modify it and do version 13 or version my name and try to use that. And the good thing is that completely independent of SMD, so you could think that you make one for another code, or even if you just use SMD, you don't need to know anything about SMD. And second, then the production is even simpler than the equilibration. You just, after the equilibration is run, you set this state. After you have a directory in which you run, then you just set up those 6 lines saying what method you want to use, and then you run.
Sorry to interrupt again, but I'm not sure I understand, but this only works unless we have major free entry barriers to overcome. Because
no, this works all the time as long as your projection can see those free energy barriers and breaks it down. So, for instance, if my projection was just trypsin-benzamine and my projection was just bound, not bound, so LMSD based. If it's less than 3 angstrom, it's bound, otherwise it's not bound. So my trajectory will become 0, 1, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1. In this case, the barrier to get out is huge. And the Markov model is not converging because you don't have, you never see the backwards. But we're not that coarse because you build things on contacts. That free energy barrier, which is 7 or 8 kilomole, you break it up in different little bumps. One hydrogen bonds forming, another one forming, the trypsin rotating, and so on and so forth. So that 7 kilocalmole barrier will actually look like something like.
Okay, but if you go up the small steps here towards this energy next,
yeah.
And you grab this point, okay, this is my starting point for my next simulation, chances it's going to go down again rather than up. Further up.
Well, we'll go up a little bit. And if your barriers are 0, your discretization is so good that your barrier are 1 kilocalmole, they will cross those barriers very quickly. And because the adaptive recognizes that it crossed that barrier because he finds another well, it will put all the simulation in the second well. So we did actually run trypsin-benzamine from bound, and we ran the adaptive. And we unbind it easily because it just moves a little bit, one hydrogen bond breaks, and the adaptive says, oh, it broke. All the 20 simulation with the hydrogen bond will broke. And then,
doesn't that require very short windows? Because if you use a long window, then
you might, yeah, it works better if you have very short window. We use 100 pico between every frame, but depending on the system, in short windows is better usually because you want to capture all these little phenomena. So the barrier is just broken down on your project, depending on your projection, and everything can work. And everything works this way. If you're really good at your projection, you could have a very fast speed up compared to. But what we see is usually a factor 20 with this sort of contact space to generate. If you use, for instance, knowing what are if you do the unbinding, you can do better than that by using the distances between the arginine or trypsin and benzamine. So you know exactly what is the dominant factor. You use the distance, so even just a little movement of that will be discretized in different beings, and so it will actually be the Markov model will discretize in a way finer way. We even break the hydrogen bonds in several bits, so it will be really fast. I don't know what's the timing, but it's fine.